Good afternoon, my fabulous chemistry students. Video number 4 of Kinetics. Take 2, because the first one did not work, and it's also potential energy diagrams. Part 2. Today we learn how to label these things up in their different parts, like the activation energy, things like the change in heat, or delta H, and the effect of a catalyst. We will get into all of that in this video, so it will be slightly time consuming. The most important parts of the potential diagram, we need to be able to tell us what those are and where they are specifically. And here's a whole list of them. The potential energy of our products and reactants, the activated complex, the activation energy in the forward direction and the reverse, the heat of the reaction, delta H, and of course our catalyst will all be done graphically for us. And here we go. Endothermic reaction. These diagrams, of course, have a positive delta H. The product side always higher than the reactant side, meaning that energy is absorbed. And so, literally, the product side is higher than the reactant side. And now, remember, if there was numbers here, I could do that calculation. Here, let me throw in some numbers. I could do a calculation of what my delta H is. But now what I need to do is label this bad boy up. So let me erase this, and we will start. Before I start, I want to be very clear. A is not always going to be the potential energy of the reactants. B is not always going to be the potential energy of the products. But the potential energy of the reactants will always be in the same place. I could call it any letter I want. It's up to you to decide where it is and label it accordingly with the problem. So in this case, it's A. So reactants are on this side. The potential energy is here. I'm going to label it A. There we go. The potential energy of the products. Products are on the right-hand side. Products. So the potential energy is going to go all the way to the bottom. This is of the products, B. Done. C, potential energy of the activated complex. That activated complex is this one piece right here on the top, the highest possible point. So the energy there is all the way to the bottom. This is now C. This is the energy of the activated complex. D, the activation energy in the forward reaction. So what we need to know is that the forward reaction starts on the left and goes right, just like every other reaction we are used to. So if I start on the left and I'm on this side, how much energy does it take for me to get where I'm at up over the hump? That's how we would define this activation energy. So we'll call that D. This is how much energy I need to get up to the activated complex. E says activation energy in the reverse direction. So that's from right to left. So that means I'm starting on this side. The activation energy would be starting here and getting up to the activated complex. That is going to be letter E in this particular case. F, the most important of all of them, the heat of reaction, delta H, which is the products minus the reactants every time. So that is going to be from this dotted line of the products to this dotted line of the reactants, and we will draw that here. This is, in this case, F or delta H. Okay. Now, the tricky part on one of these graphs also is that this A can be drawn. Let's see if it'll grab it. This A can, wait a minute, why did it erase? I can draw the A on this side, because importantly, it's from this dotted line, which is the reactants, to the bottom. So delta H could affect be drawn here or in the middle. We can't get hung up on where they're drawn. It's what they're identifying from what side to what side, or from what line to what line, is what's going to make it key. Okay, so activated complex is the highest energy point of the reaction. It's where the arrangement happens in the chemical reaction. All chemical reactions will have them. Exothermic, heat is given off. So we have a negative delta H. I always end up with a lower energy because energy is being released. And now notice the reactants are higher now. The reactants start at 60 and the products are down to 20. So the higher to the lower, exothermic, energy is given off. So real quick, we're going to need to be able to do that piece, exothermic, endothermic, just by looking at the graph. Is it start high and go low, or does it start low and go high? And we need to get that right every time. So I'm going to go through this labeling up. It's very much the same. I didn't switch the letters around, although I could have. I'll do this one just a wee bit faster. A, potential energy of the reactants. Reactants are on the left. That's A. B, potential energy of the products. Products are on the right. Notice those lines basically, or the magnitude of those lines just switched. C, potential energy of the activated complex. Here's the activated complex. So this is my C. D, activation energy forward reaction. That's here. E, activation energy in the reverse direction. That's this big one, starting on the right and going left. And then, of course, F, and I'm not going to scroll, is the delta H, which is in between the products and the reactants. Delta H, or in this case, F. Okay? Good. We just learned all the major parts of a potential energy diagram. So question, if a catalyst were added to the above diagram, which letter or quantities would change? Well, let's go back to that diagram so we can see what it would look like if I added a catalyst. So I'm going to erase all this stuff so we can key right in, and I'll change colors to red. If I add a catalyst, every time the reactants stay the same and the products stay the same in terms of potential energy. But what happens is my pathway changes. So you'll see a dotted line similar to that. Now, if that line changes, my activated complex changes. So my potential energy of my activated complex changes. But more importantly, this activation energy in the forward reaction that, what was it? It was D. Yep, D. The D would change. So the activation energy in the forward reaction would go from what was here down to the blue one, which is smaller. So if I need less energy, I can go faster. And that is how the adding a catalyst will affect my rate of reaction. So which ones would change? Most importantly, the activation energy specifically in the forward direction. But believe it or not, it would also in the reverse. So both of them account. The potential energy of the activated complex would also change. So there's three that would change. Next question, how does the addition of a catalyst change the heat or delta H? So let's go back. My reactants stay the same, my products stay the same. So did this piece, the delta H, change at all? The answer is no. So it didn't change. What are the benefits to adding a catalyst? It speeds up the reaction. By providing an alternate pathway. So now that we've done this homework and the homework before number 3, we can do practice packets 5 through 8. We can go on to Castle and then do our prep number 2 quiz, and then after we're done with our prep number 2, we can actually take the second quiz. So we are good to go. On to homework 5 when you get time. See you in class tomorrow.